There we go. Okay, so are there any questions over homework problems? Anything that I can go over or clarify?
Will you have office hours today?
Well, I'm not on campus, so not technically have office hours. I can try and do Zoom later. Would that suffice?
Yes, that would work.
Okay. Yeah, I mean, I'll do it. I'll send an email out to everyone, and basically I'll just kind of I'll have my phone, and then I'll give you my cell phone number. If you want to meet on Zoom, just text me. I'm not going to sit in front of the computer for 2.5 hours waiting for people to show up. So I'll just have people text me if they want to meet me. Okay. Anything else? Everyone can see the screen, right? The standby will start shortly. Yes, yes. Okay, thank you. Let me got to do one thing here. Figure that out. Okay, so today we're going to talk about continuity. It's kind of good that we're doing this Zoom because there's a lot of visual here, and then also this is not a major part of the class. I mean, continuity is important, but it's not one of those things where if you don't get this, you're doomed the rest of the semester. All right. So let's get into that. Oh, the wrong one. Here we go. Okay, so we're going to cover 1.5. That'll finish up chapter 1, and then, like I said, we'll start chapter 2 next time. All right. So when it comes to this idea of continuity, it's a very, very simple definition. Like the definition is right here. And when you read it, there's not much here. All right. But understanding what it's saying is important. All right. So it says here, a function f is said to be continuous at the value x equals a if this is true right here. So let me try and explain a little bit what this is saying. I'm going to copy this and paste it over to this other page. So there's kind of like two sides to look at here. The left side is saying that when we look at things from a calculus perspective, we have a limit and it exists. So that means when we look at the graph of the function and we approach the value a, right? And when we approach some value a, that the limit exists, which means that from both directions, the graph is going somewhere. So it's going from the left, and from the right, it's going to the same place. Now, what we learned before is that for the limit to exist, we don't care what's happening at a, right? We could have a hole here. We could have a dot up here, and that we would still have that this limit exists, right? We would still have that regardless of what's happening at a. But the definition of continuity says, okay, not only does the limit have to exist, but it must be equal to the function's value at a. Now that's the college algebra perspective. So what we need is for both the limit to exist and that limit has to be equal to the function's value there, which means I cannot have a point up there. I can't have a hole. I actually have to be filled in solid here. And so when you think of continuity, you're basically saying there's no gap there. At that point, there's no gap. The function comes in, and when it actually closes in on that point, you have to fill that point in. And then the function is continuous there. Continuous, like it keeps smoothly going through instead of having something weird happening. So that's the general idea. Let me get back to the notes. Again, this will start to, if you're still confused, just give it time. All right. So here's a picture for us to look at. So if you look at this and you look at the x value of 2 here, I'm asking you, is this function continuous at 2? So what do y'all think? Feel free to unmute yourself. Is this, okay, so why is it not continuous at 2? Why not?
Has an open circle at 2, so
Okay,
it has a opening inside the line.
yeah, so for continuity, I'm gonna put CONT, continuity at x equals 2 means that the limit as x approaches 2 of this function must be equal to f of 2, right? So all I'm doing is using that definition I just gave you, right up here, this definition, right? To be continuous at 2 would mean that that has to be true. So all I did was replace the A's there with 2, right? Let's go back and look at this. Where was I? Right there. Okay. So tell me, y'all are saying that it's not continuous because there's a hole there. But in terms of this definition, does the left-hand side make sense? Does the limit as x approaches 2 of this function exist? Yes or no? Just the limit, not the continuity, but does the limit exist at 2?
Yes.
Yes.
Yes. Right? Because we're going in from the left side and the right side, we're going to the same point. So left side's not a problem. We had the limit, that's fine. What we don't have is the other side, because the other side, what is f of 2? What is f of 2 here?
It's
The function?
oh,
What's
undefined
the
at 8.
value of the function at 2?
Undefined.
Undefined, right? So this is undefined, right? And we're asking ourselves, is that equal to the limit? And what's the limit? Can y'all tell from the picture what it looks like we're approaching?
8.
8, right? So the limit of the function is 8. And the question is that equal to undefined? Well, it's not, right? So therefore, you don't have continuity. Questions?
So what is the parameter if it is continuous? Like, how do we know?
This left side, the limit here, will be equal to the function's value there. If these two sides are equal, you have continuity. We'll do another
I see.
example. We'll do another example. Let me see. I'm trying to remember. I haven't used Zoom in so long, and I have this like mouse that has, it's like a gaming mouse, and I have all these like shortcuts on it. Let me see if I can remember some of them here. I think this clears the screen. Oh, yeah, I remember. All right, good. Okay, let's look at this one. Give me just a second. Okay. All right, so take a look at that for a moment. I'm gonna write some stuff here. This is 2. This value up here is, looks like 8 again. So what do y'all think? Is this function continuous at 2?
Yes.
Yes, you think so?
Yes.
So let's check for continuity at x equals 2. It means that the limit as x approaches 2 of this function must be equal to the value of the function at 2. So what is the limit, everyone? Or anyone, I should say. What's the limit of this function as you approach 2?
8.
8. It's 8 again, right? Because when you come in from the left and you come in from the right, both of those are approaching, right? Remember, it's a limit. We don't care what's happening at 2. We're asking what's happening near 2. So as you come in from both sides, it appears that the function is approaching 8. And the question is that equal to the value of the function at 2? Well, what's the value of the function at 2?
6.
6, right? 6. Are those equal?
No.
Right? So is this continuous at 2? No, right?
No.
We need to have those two things equal to one another. So I didn't put this on the other one. The answer here is no, right? On the previous one, it was no. Let's look at another one. Same question. Is this function continuous at 2? What do y'all think?
Yes.
Yes.
Yes. Can you explain why, Marcus?
Um,
Like
The-
using the definition, can you kind of explain like why?
the limit is equal to the function.
Yeah, the limit is equal to the function's value there, right?
Yeah.
So what is the limit? Well, everyone,
8.
8, right? Same thing. It's approaching 8. But that's what the function is actually defined to be there as well, right? It's defined to be 8 as well there. So they come together to a point, and that's what continuity at a point is. This making sense, everyone? Anyone have a question? Let me ask you about, let me change the problem up. Let me go to the value of 1 instead. Okay, so imagine now I'm asking you, is this continuous at 1? Well, you go up here, right? And do y'all agree that there's a dot there? I mean, the fact that it just keeps going through, it's implied that there's a dot, right? So are we approaching, do we have a limit from both sides going to the same place?
Yes.
Yes.
Is the dot when we get there, is it filled in?
Yes.
Yes, so it'd be continuous at 1 as well, right? Would it be continuous at 3?
Yes. Sir.
Yes. Do you see anywhere that it would not be continuous? I mean, of course, we're going to go off the graph keeps going. We don't know what it does over there, but from what you can see here on the screen, do you see any places where you would not have continuity?
No.
Yeah, it looks like there's nothing. I mean, everywhere. It looks like it's continuous at every point, right? Let me go back up. Let me go back up to this one. We already said that this function is not continuous at 2, right? How about other places? Like, would this one be continuous at 3? What do you think?
Yes.
Yeah, it would, because we come in from the left, we come in from the right, it's headed to the same place and it's filled in there. You could go to any point you want, and we're going to have continuity at those points. The only place on this function where we don't have continuity is right here at the value of 2. Okay, so right now, as we're talking about continuity, we've defined continuity as something that's happening at a specific value of x. But you can look at different places on the function and ask, is it continuous there? Is it continuous there? Is it continuous there? And keep looking at all these places, right? Can somebody kind of tell me, like, if you're trying to explain this to like an elementary school kid or something, what continuity is? Like, when you look at the graph, what is, if you were continuous everywhere on the graph, can you kind of tell me what that graph would, like, what's its main characteristic? Think about that for a second. If you're trying to explain this to a kid, right? Like, yeah, a function that's continuous just means what? There's one that's continuous. There's one that's not. There's one that's not. Go ahead, Lewis. What did you say?
Oh, I was gonna say a graph, or it's a continuous line, is one that doesn't have any breakpoints or openings inside of it.
Exactly. Exactly. So if you're explaining this to a child, you could say a continuous graph would be basically a graph that you can draw without picking up your pencil, right? Like, I can draw this and never pick up my pencil. To draw this one, I would have to pick up my pencil at some point. At some place I would have to. Even here, if I'm going to draw this, I would have to like jump over that point. So I had to pick up my pencil and then continue. So I'd have a hole. So a very simple way of looking at continuity is to say, oh, well, if you can draw it without picking up your pencil, you're good. Like, it's continuous. Okay, let's move on. Let me make this a little bigger. All right. So like I said, we can see the basic idea is that we can draw the function without, draw the function with the pencil without lifting the pencil, okay? And then it's continuous. All right, so if continuity has a definition, then we have this other definition called discontinuity. And discontinuity just means that you're not continuous at some point. So when we look back up at this function was continuous pretty much everywhere. This one was continuous everywhere except 2. So what we could say is that this function is discontinuous at 2. Same with this one. We could say this is discontinuous at 2. So really, this is like just a language thing. We're just defining some things, and we want to understand when we say something like that, what we mean. Okay, when it comes to discontinuities, there are 3 types of discontinuities that you need to be aware of, all right? A jump discontinuity, an infinite discontinuity, and what we call a removable discontinuity. I'm going to show you an example of each one of these. So the first type is this thing called a jump discontinuity. So imagine you're drawing with your pencil, and at some place, your graph jumps, either up or down. There's a break in the graph. We call that a jump discontinuity. Any function that has a jump in it can never be continuous at that point. Whatever that point is, let's just call it, in general, let's just call that A. Do y'all see why this would not be continuous or be discontinuous? Can somebody explain it to me in terms of the limit, this limit definition? Can somebody tell me what would go wrong at a jump?
Because the limit from left to right is, so the left is going to be 2, 8, and then from the right is going to be 2, 5, I believe.
Exactly. So Matthew is pointing out that if you have a jump, the left-hand limit and the right-hand limits will not be equal, right? Therefore, the left side of this would be what? If you have a jump. What happens to a
Undefined.
limit when the left and right aren't the same? What do we say?
The limit does not exist.
The limit doesn't exist. Exactly. So the left side of this would be does not exist, right? And then we'd be asking ourselves, is that equal to f of a? Well, f of a here, what is 8, right? Does not exist doesn't equal 8. So there's no way these could ever be equal. So therefore, you're going to have discontinuity there. Questions? I have another one I want to give you. That's actually not in my presentation here. Let me give you, how about this one? What if we have a graph that does this? Let's say at A, we have this, and then we have that. So there's a jump, right? So we're asking ourselves, is the limit as x approaches A of f of x, is that equal to f at A? So somebody tell me what the left side of this is.
Does not exist.
Does not exist, right? Everyone clear on that? That doesn't exist because from the left and right, we're going to different places. Somebody tell me what the right side of this is.
Undefined.
Undefined. Now, do you remember when I told you in the very beginning, when we were talking about limits, that we will say does not exist for limits and undefined when we're talking about algebra stuff at a single point, and that they aren't the same thing. Like, I don't want you to think that they're the same thing. This is exactly why. Because if you thought undefined and does not exist were the same idea, then you would actually maybe think that these are equal. But they aren't. To say that a limit does not exist is not the same as saying that a function at a point is undefined. So these aren't equal. Therefore, this would be discontinuous at A. All right, let's get back to the notes. All right, that was a jump discontinuity. The next discontinuity is this right here, an example. This is called an infinite discontinuity. And I want you to understand that this function here goes up. So it's almost like you have a vertical asymptote here. It just kind of blows up on both sides. So my question is, is this continuous at, let's say, 2 here? So who wants to tell me what the left side of this is, and who wants to tell me what the right side is?
The left would
side
be-
is infinity.
I think I heard left side's infinity. Was that you, Dalton?
Yes, that was
Okay.
me.
And Louis, I think you said the same thing.
Yeah, my bad.
Okay.
Sorry.
No, y'all are good. Y'all are good. I appreciate the reply. I might have to start calling on people since they're in the other room watching Netflix or something. I kid. All right. Infinity here. All right. Somebody else. Give me the right side. What's f of 2?
Infinity.
Careful. What's the value of the function at 2?
5.
5.
Oh, five.
5, right? See, I have a dot there. The value of the function at 2 is 5. You see that, Matthew?
Yes, sir.
And always keep in mind, everyone, if you're ever asked what the value of a function is at some point, you can never have an answer of infinity. You can have infinity if you're talking about a limit, but you can never have infinity as an output of a function. Like you plug in 2, you get infinity. We can't have that. We could only have undefined or some number come out. But we know that the left and right hand sides are both going to infinity. The value of the function at 5 is, at 2 is 5. So of course, these aren't the same, right? Now, I'm curious if anyone can tell me why we will always have a discontinuity whenever we have a vertical asymptote. I want you to think about that for a second. I want to see if we can get more people to play here. If I tell you that our function does this, right, at A, or maybe it goes the other way. Maybe it, at A, it goes down to negative infinity on both sides. Can someone explain why we can never be continuous when this happens?
Because
Go ahead, Ash. You unmuted and then you muted again.
sorry, it's because whenever you get to f of a, it's going to be undefined.
Exactly. So, well, it could be undefined, right? But it could also be a dot. Like I could put a dot here, but either way, Ash, it will never be equal to what?
It'll never be equal to infinity. or
Yeah, it'll
negative
never
infinity.
be equal to what the limit is, which is either infinity or negative infinity. So in this case, the limit side equals the function's value there. Sorry, that's sloppy. In this case, it goes to infinity. In this case, the limit goes to negative infinity. But the point is that can never be equal to the function's value, because like I just said, the function's value can never be infinity. It could be a number, or it could be undefined, but it can't be infinity or negative infinity. So you're never going to have continuity where you have vertical asymptotes. Let me give you one last one. This one, let's say it goes up on the left and down on the right. Do y'all see that wouldn't be continuous because your limit doesn't even exist? Like from the left, you're going to infinity, the right, you're going to negative infinity. So not only does the limit not exist, you're never going to get it equal to the function's value. So this is like really bad. This type of discontinuity is called an infinite discontinuity. That's the second type. So we have the jump, we have the infinite. Questions? All right. The third type is called a removable discontinuity. And this, when I was learning this, I was like, that's kind of a weird name for a removable discontinuity. removable discontinuity. What do we mean by removable discontinuity? So a removable discontinuity really just means that we have a hole. Okay, do y'all see that we have a hole there? And that creates the discontinuity, because when we get to the definition, what's wrong with the definition if we have a hole? Where do we have a problem with this definition? Left side or right side?
The right side.
Right side, because the right side will be undefined, right? So that's why a hole causes a problem. Now, what does anyone have a guess as to why they call it removable? I don't expect anyone to get this, but you never know. Why would we call this removable? Let me give you a hint. Would it be easy to fix this?
Yes, because you can just remove that one open circle.
Yeah, if we just fill that circle in, right, with a dot, it would be a simple, we could tweak the function and just define it at 2 to be 8, and we would fix the problem, right? So let me see if I can't, I'm not going to be able to come up with a function. Hold on, let me think about this. I'm going to actually, you know what I'll do? Give me a second. I'm going to just bring up the code for this, and then I'll know what function I used. X negative x cubed plus 4x squared. Okay. So this is the function. No, that can't be the function. Hold on. You know what? At 2, I get 0. So sorry about that. I should have had this right. I didn't think I was going to talk about this. So let's see, x squared minus 4 over x plus x minus 2. Okay, there we go. So this right here, that function right there is this function that we're looking at roughly, at least this part right here with the hole in it. Do you all agree with this function that I cannot plug in 2? If I try and plug in 2, I get 0 over 0, don't I?
Yes.
Yes.
Okay, now, so if I define that, I want everyone to see f of 2 is undefined. Now, what is the limit as x approaches 2 of this function? So these are two different questions I'm asking, right? The first one is, what happens if I try and plug 2 into the function? Well, I get 0 over 0, and that's undefined, right? But if I take the limit, I get 0 over 0, and what do we do? If we have a limit and you see 0 over 0, what are we going to do?
Algebra trick.
Algebra trick. Okay, who sees the algebra that I would do to calculate this limit?
Squares. Difference of squares.
Difference of squares on top. Good. So I do x plus 2x minus 2. That would cancel with the x minus 2 there. And now plug in 2 here. And you get 4, and 4 times 2 is 8. And isn't that what our limit is? Y'all see that when we approach 2 from the left, we're headed to 8. When we approach 2 from the right, we're headed to 8.
Yes.
So,
Yes.
what I'm trying to get you to buy into here is that this function right here is a pretty good representation of what we're seeing. The reason we call this a removable discontinuity is that I could, like I said, tweak the function just a little bit, and I could fix the whole problem. And here's how I would tweak it. Here's how I would remove the discontinuity. I would do this. I would, let me see, I think I can change the color of my pen, yeah. Okay, so what I would do is I would define a new function. Let me call it g of x. And here's what this function is. It's actually two different functions. Back in college algebra, we called these piecewise functions. The first part of this function is the function we were just messing with. And that's the function we will use if x is not equal to 2. So do you all agree that this function draws what I see here in red? It draws this. So far, it draws all of this, and it draws all of this. But at 2, what I'm going to do is define it. If x is 2, I don't want you to try and plug 2 into this. I just want you to just spit out the number 8. And if I define this new function this way, it will come in and fill that hole in, and you will have removed the discontinuity. So anytime you have a hole in a function, you can always remove it by defining a new function where you fill that hole in with whatever you need to fill it in with to make it nice and smooth, where you don't have to pick up your pencil. Now, if you're still a little unclear on that, that's okay. Let me have you look at this. Look at the infinite discontinuity. Is there an easy way to fix this? Well, no, I mean, there's not. You would have to completely change the look of the graph to make this be able to draw it without picking up your pencil. You would have to, I don't know, do something like this to make it connect and then come back down. But see, you'd have to remove all that. And now it's not the same function. It looks completely different, right? It's not an easy fix like just filling in one point. We'd have to adjust the whole graph. Same with this one. To fix this one, you're going to need to completely do away with this and make this curve come in here like that. And now you've made some major adjustments to the graph. It's not just a simple thing. So that's why we call that one case where we have a hole, we call it removable, because there's an easy fix to just fix that one point. I hope that makes sense. It's not a huge thing. The main takeaway for you is that there are 3 types of discontinuities: jump, infinite, and removable. That's it. That's all you need to know. And you need to know what they look like. Questions?
Will we have to know how to or will we have to define a new function
No.
if we ever encounter?
No, good question. Yeah, I would never ask you to hey, redefine this function so that it's continuous at 2. Maybe as a bonus, but I wouldn't ask it on a test. Okay. Everyone's clear on continuity? As clear as you think you can be at this point? No questions, clarifications? Okay, thank you. All right, so now that we've established that, we have it's still this discussion about continuity, but we're going to talk about what's called left and right continuity. And left and right continuity are weaker conditions than continuity. Continuity requires that we come in from both sides and that we have a point right in the middle of those two sides coming together, right? That's continuity. Very, very strong conditions, both sides to a point. Left and right continuity only require that the limit be coming in from one side to a point. So first, some notation, right? And definition: left continuity at a point. What does that mean? Well, the function is said to be continuous from the left if at x equals a, if the limit, notice this, as x approaches a only from the left equals to the function's value at that point. So we only need that when we come in from the left side, we're going to a dot. We don't care about the right side. That's left continuity. Right continuity is the opposite. It says, okay, if you come in from the right side to a point, then you're right continuous. Here's a picture. So look at this here. Let's look at what's happening at 2. It says here, I'm telling you, it is continuous from the left. The reason why it's continuous from the left is that as we come in from the left side of 2, we are approaching the value of 8. But that's also the function's value there. At 8, we've got that dot. So they're equal. I'm going to click on this. It'll show that explanation over here. So the limit as x approaches 2 from the left of the function is 8. The function's value at 2 is 8. And so it's left continuous because those are equal. Is this function continuous at 2? I just said it's left continuous, but is it continuous?
No.
No, it's not continuous.
No, right? It's not. Why?
There's still a jump and a
Yeah.
hole at 2.
Yeah. There's a jump, right? So when we look at it in terms of continuity, like I just said, continuity at a point is a very strong condition. It's got to be from both sides. So even though this is continuous from the left at 2, it is not continuous at 2 because you've got the jump. Look at this one. This one is right continuous at 2 because as you come in to the right of 2, you're approaching some point, and that's exactly what it's filled in to be. So you've got right continuity at 2, but again, you do not have continuity at 2 because of the jump. Let me go back up here. Look at that one again. I want to talk about what's happening at 2. Is this left continuous at 2?
Yes.
Yes. Is it right continuous at 2?
Yes.
Yes. Is it continuous at 2?
Yes.
Yes. So continuity at 2 forces left and right continuity to be true as well. That's why I'm saying continuity is a very strong condition because it requires both left and right continuity to be valid. Could you have this though? Wait a minute, I'm gonna see if I can trick you. Could you have this? Here's A. Is that left continuous at A?
Yes.
Yes. Okay, now, is it right continuous at A?
Yes.
Yeah.
So is it continuous at A?
No.
No, because it's different f of x's.
Okay, so what's wrong with this? Why is this? Because I just said that if you're continuous at A, then that forces left and right continuity to be true. Well, what about this? It's left continuous at A, right continuous at A, but not continuous at A. So what's wrong? There's something wrong. I've kind of tried to slip something by you here.
Is that a function at all?
Very good. It's not a function. At A, it's not a function. Because at A, you fail the vertical line test, don't you? You hit the graph in 2 places. So this is, I cheated. That's why when we talk about continuity, we're talking about continuity of functions. We're not talking about continuities of graphs of random things. It has to still be a function. Once we know we're talking about functions, then we can talk about continuity. So I tried to cheat. Ash caught me. Good job.
So that's not continuous, what we just saw?
It's not a function. So we can't talk about continuity. Notice on all these definitions, let me go back up to the original definition of continuity. See the first thing? A function, f, right? We have to have a function. If we don't have a function, we can't talk about continuity. Make sense? I'm
Yes.
never going to try and trick you and give you something that's not a function. I just want to point out that, you know, we have to be a little careful whenever we read a definition. Like especially in math, every word counts, like in a definition or in a theorem. If there's something stated, it's there for a reason, right? We don't leave things out of definitions because that can change everything. Okay, so we've got left and right continuity. All right, so this we've already, no, this we have not talked about. So now we talk about continuity on an interval. Okay, continuity on an interval. So an interval is like a segment of numbers on the x-axis, right? This interval. And what we want to see is, what does it mean for a function to be continuous on an interval? So look at the picture. We're looking here at this interval 1, 3. So that's between 1 and 3 on the x-axis. And the question is this function continuous at every point between 1 and 3? What do y'all think? If you go to any point in here and look at your graph, are you going to be continuous at all those points in there?
Yeah.
Yes.
Yes.
Yes. Okay. What about at 1 though? Let me challenge you. What about at 1? Ooh, that should have been a different color. There we go. What about at 1? Are you continuous there? What do y'all think?
No, because it's not from the left
No.
and right.
Yeah, what about the left, right? Well, sorry, let me say it again. What about the left, correct? Like, what's going on from the left? Do we have left continuity? That's a question mark. Let me try it again. We don't even have a graph to the left, do we? So can we really talk about continuity at 1 if we don't have a graph coming in from the left? And then at 3, yeah, it's continuous from the left, but what about from the right? There's no graph. So this is where we have this definition, all right? I'm going to clear this out. Look at this definition carefully. A function f is said to be continuous on an interval if it is continuous at every point in the interval. Let me circle that. At every point in the interval, right? In being the key word here, in the interval. That means if we look at any point inside the interval, we should be continuous. Go to any point here and we'll be coming in from the left and right. Any point coming in from the left and right, we've got continuity. So you can draw it without picking up your pencil. But at the left end point, that means this point right here, you only need right continuity. You only need it to be right continuous. And at the right end point, you only need it to be left continuous. And that takes care of that question of, well, what's happening from the left? What's happening from the right? When you talk about continuity on interval, you only need continuity on the inside, and on the 2 endpoints, you need right continuity and left continuity respectively. And then you can say it's continuous on the interval. All right, some theorems. So let's say that you're given 2 functions, all right? Function f and function g. And let me tell you that they're both continuous, all right? You can draw both of them without picking up your pencil at some point. This theorem says that if we combine these functions together, we still maintain the continuity. Now, this is a theorem, so I'm not going to prove this. You're just going to believe this. So if I take 2 continuous functions and add or subtract them, I'm going to get a continuous function. If I multiply a continuous function by a number or scale it, which stretches it out, it's still going to maintain continuity. If you multiply 2 continuous functions, you still have continuity. You don't lose it. And then if you take the quotient of 2 functions, you will maintain continuity as long as the denominator is never 0. If the denominator is 0, then you'll lose continuity. I'll show you, I'm going to show you with some visuals, but this is just a theorem saying that, you know, we can do this. All right, so now this is a big one, this note here. What functions that you've learned in your life are continuous, right? Like, what can we say is continuous and what can we say is not? So if we go back and look at college algebra, all polynomials are continuous everywhere. Think about parabolas, lines, polynomials that would go up and down, right? Left and right hand behavior that we had. All of those, you never had to worry about picking up your pencil. You could just draw it. So this theorem says, yeah, as you would expect, all polynomial functions are continuous. So there's an example of a polynomial function. And of course, this is like an arrow, it keeps going up to the left and keeps going down to the right. Go to any point on that graph and you are continuous. The second note says all rational functions are continuous on their implied domains. This is important. Implied domain is important here. Let me give you an example of a rational function. That's a rational function from college algebra. With rational functions, sometimes we have these vertical asymptotes, right? What this theorem is saying is that, yeah, we understand that we've got infinite discontinuities here. We have it happening here. There's an infinite discontinuity. Here, there's an infinite discontinuity. But those 2 points where that's happening are not in the domain of the original function. So you could never plug those x values into the original function. Therefore, when we look outside of those 2 points, when we look at the domain of the function, which is in the blue here, anywhere that the graph can be drawn, you can draw it without picking up your pencil. So if we just look at this section over here, you can draw that without picking up your pencil. This section can be drawn without picking up your pencil, and so can this one. So individually, those 3 sections are continuous. Questions? What about trig functions from pre-cal? Same story. That's a sine function, right? That's continuous. You can draw it without picking up your pencil. Let me give you another example that's actually not here. Hey, where did my Desmos go? Let me do the secant function. That's the secant function from pre-cal. And the secant, remember, is the reciprocal of cosine. So if you look at this, everywhere that the cosine hits the x-axis, we have vertical asymptotes. Right? So if you were to think about what the domain of the secant function is, as long as you're in the domain, when you draw that graph, it's going to be continuous. So that little U-shaped piece of the graph there is nice and smooth, no jumps, no breaks. This little U shape there is nice and smooth, no gaps, no jumps, no breaks. So within each of these little sections, we've got continuity within each of these sections. If we ignore the vertical asymptotes, which again, those points are not in the domain of the original function. So I'll go back to the note just to clarify. All trig functions are continuous, not everywhere, but on their implied domains. And then exponentials in logs. There's an exponential function. You can draw it without picking up your pencil. And there's a log function. You can draw it without picking up your pencil. All right. We're almost to something interesting here. This other theorem says that if you compose to, well, you know what, before I do that, let's do this. Let me go back up to this. You know how I said if you add 2 functions together that are continuous, you still have continuity? Or if you multiply them or divide, you still have continuity? Let me show you that. I'm going to start over. I'm going to take 2 continuous functions. So first, I'm going to graph sine x. Everyone agree that's continuous everywhere? Anyone disagree? We're good?
Continue.
Okay, I'm going to draw you another one, x cubed. Let me do x cubed minus x there, a little more interesting. Okay, so those two functions by themselves are continuous. Now let me do something. Let me add them together. So what if I did x cubed minus x, and then I added to it the sine x function? That's the one in black. Does that look like it's a continuous function? Still looks like you can draw it without picking up your pencil, right? Okay, let me go back. Let me, instead of adding them together, let me multiply them. So if I take those two and multiply them, here's what it looks like. Oh shit, it's crazy looking, right? That's a crazy looking function. That's really crazy looking. Oh, that's actually pretty awesome. Okay, there it is. Now, if you try and draw that, you can do it without picking up your pencil. Guaranteed. There's going to be no jumps. There's going to be no infinite discontinuities. There's going to be no removable discontinuities. How do I know that? Because the theorem says if you start with two continuous functions and multiply them, then you're going to have a continuous function. Now, division is a little bit strange, okay? So if I do division, watch what happens. If I divide, no, I didn't want that. There we go. That's what happens when we divide. And let me zoom out because there's got to be more picture here. Hold on. Yeah, that's crazy looking. Well, that's pretty awesome, actually. Okay, this is the graph of this function. We have a ton of discontinuities in here. If I look at this graph here, anywhere that the sine function is 0, we would have a discontinuity. But if you look outside of that, in each of these sections individually, you can draw them without picking up your pencil. That's what the theorem says. Like throwing out any place that causes the denominator to be 0, all the other places you should have nice and smooth. No jumps, no breaks. And then this last theorem, which I said, I kind of paused us on here. Where is it? This last theorem says that if you try and do the composition of two continuous functions, you're still continuous. So I'll show you that with this as well. So let me go back to the main view. What I'm going to do is I'm going to take the sine function, but instead of multiplying it times the other one, I'm going to plug the other one into the sine function with that's composition. And you can see that when you draw this, even though it's crazy, you still can draw it without picking up your pencil. So it is continuous everywhere as well. All right. I think things are going okay. Does anyone have any questions for me?
Was that last one considered continuous, the one before the one that you just did?
The one that I did when I divided by secant or by sine?
Yes, sir.
It's only continuous where it's defined. So like if you tried to plug in a number and you got division by 0, it wouldn't be continuous there. But if you go to any other point where it is defined, it would be continuous at that point. So as long as the point that you're trying to plug in is in the domain of the function, then you're guaranteed continuity.
Okay, I got you.
The condition though is that the numerator has to be a continuous function and the denominator has to be continuous. Then when you divide them, they're continuous as long, again, as the number you're plugging in is in the domain. All right, we've come to a very, very important theorem, not only in this class, but in mathematics, period. One of the most important theorems. It's a pretty, well, I'd say it's a pretty straightforward idea. Most students have no problem understanding, like, yeah, that makes sense. But we use this theorem a lot, especially computer science majors. you know, computer science people use this theorem when they're programming a computer to do things. So let me get to the theorem first, and then we'll actually, you know, get back to the usefulness of this. All right, so here's the theorem. It's called the intermediate value theorem, and I abbreviate it IVT, intermediate value theorem. And here's what it says. First, suppose you have a continuous function, right? So you got this function and it's continuous on a closed interval. So what do I mean by continuous on a closed interval? I mean, we have this situation right here where you have a function that you have, it's defined on an interval. It's continuous at every point in that interval. At the left endpoint, you are right continuous, and on the right endpoint, you are left continuous. Let's say we're starting with that, okay? That's what we have, a continuous function on a closed interval. Now it says, we also have f of a is not equal to f of b. So I'm going to draw that for you on the side. I've got this function. It's defined between some value a and some value b. Whatever the value is at a, it is not equal to the value at b. So the height of these 2 points are not the same. That's what this is saying. And when I draw, I have to draw it so I don't pick up my pencil, right? That's what we're starting with. I'm saying, let's act like we have a function that is just like this, continuous on that interval, and that the 2 endpoints are not at the same height. Then the theorem says, okay, well, let n be any number between those two values, f of a and f of b. So I'm going to go back over to my picture here. I'm going to pick some value, capital N, that is somewhere between the height of this point, f of b, and the height of this point, f of a. So do you all agree that if f of a and f of b are not at the same height, then there should be a number, you know, there's a bunch of numbers between them, but I could just pick one of them and call it capital N, right? As long as they're at different heights, I should always be able to find a number. It doesn't even have to be right in the middle of them. It could be any number, right? So the theorem says, all right, we started with that function. Let n be any number that's between f of a and f of b. Then here's the main conclusion of the theorem. Then here's what we can say. There must exist a number c in the interval a, b such that f of c equals n. What the hell are they talking about? They're saying that there must be some point c in here that when you plug c into the function, you get that n, right? There's some value of c that gets mapped through the function to that value n, and that should work for any n you ever pick. I want to do it again. What? I have a function on a closed interval. Doesn't matter what it does as long as I don't pick up my pencil. The value of the function at a, I'm sorry, that's the value of the function at b. This is the value of the function at a. That's all given. Now, somebody can pick a number. Now I'm going to move my cursor up and down just randomly here. I'm going to wait for someone to tell me stop.
Stop.
Okay, right here. All right, that's a random number between those two. Do you all agree I should be able to find some number now somewhere in here? There should be some number that when I plug that number into the function, it should hit that value n. Right? It's there. Do y'all see it? Where is
Yeah,
it?
I see it.
Is it close to the A or is it close to the B? Is it in the middle? Where is it?
Close to
Close
the
to
B.
the B.
Close to the B.
Close to the B, right? Somewhere over here. I don't know, maybe the easier way would be to go backwards, like go here like this. See where it hits and then come down. You see? The theorem says you're guaranteed that you can find that value C. That value C is always going to be there. As long as you started with a continuous function between on a closed interval and that the two endpoints weren't the same. Now I have more animations to show you, all right? So here we're going to take this continuous function on this closed interval. All right. We make sure that these two endpoints aren't the same. And now I'm going to pick a value of n somewhere between here. Let me do that one right there. I'm going to give you a moment to see if you can figure out where the C is that gets me to that point. So here it comes. There, right? We go over, we go down, and we will find that value. Notice that value, C equals 4.67, lives between the two endpoints of the graph. Let me back it up. Let me do a different value of n. How about down here? This one's kind of interesting. Do y'all see that? Y'all tell me, is there one answer here or are there more than one answer? Is there more than one answer for that n?
More than one?
Yeah, there's more than one. Look, I could go backwards to here and then, well, let me do a different color. Backwards, and then I go up, and that would be a C, right? But also I could have gone here and up, that would be a C, that would work. And then this from here up would be a C. So there's actually three inputs, three different values of C that I could have plugged into this function. All of them would spit out that same n value. The theorem says there exists a number. This means there exists at least one. Does the theorem say that it's only one? No, it says there must exist a number. Could be more than one number, but there has to be at least one. Now, for this theorem to work, you have to have continuity. And let's see why. Look at that example right there. This function is not continuous. It has a, what kind of jump, I already gave it away. A jump discontinuity, right? You see that? So if I try and cut this function off like this between 2 points, even though the endpoints are not the same, the height here and the height here are not the same, do y'all see that I would have a problem if I try and pick an n right here? Do y'all see right there? There's no place that the function actually gets to that point. There's nowhere I can pick on this part or on this part that's ever going to hit this line. The graph will never hit that line. So therefore the function will never take on that value. So it fails. The theorem fails here. Why? Why does the theorem fail? The theorem's supposed to always work. So why does the theorem not work here?
It doesn't work for any n value between f of a and f of b.
Yeah, it's not working, right? But the theorem says it should always work. So what's going on here? Why is it, what is the first condition of the theorem?
It's supposed to be continuity.
It's supposed to be continuous on that closed interval, isn't it? I just gave you an example of a function right here. This function, is it continuous on this closed interval? No. So if you throw out the continuity, the theorem no longer applies. I'm just trying to point out to you how important continuity is for the theorem. All right. So we're about to do a pretty interesting problem, I think. I'm just going to kind of recap what the theorem is saying. The theorem says that if you have a function that you can draw without picking up your pencil, and you have two endpoints that are different, then the function must take on every value between those two endpoints. I really want this to get through because this is the crucial part of it. Let's say you have a function at A, it's here, at B, it's here, and you draw it without picking up your pencil. That means every value, let's say this is 6, and let's say over here that's 2. What I can tell you is as long as this is a continuous function on that interval, that this function is going to eventually at some point hit 2. It'll hit 2.1, it'll hit 2.5, it'll hit 4, it'll hit 4.67. It'll hit pi, right? Pi is in here, 3.1415. Every number between 2 and 6 is somewhere on that graph. Somewhere on that graph, I've got values that correspond to any output between 2 and 6. Somewhere in here. I don't know where they are, do I? I just know that they exist in there. Any questions? We're about to have the big moment here, like the big takeaway of this. You ready? Here we go. All right. Use the intermediate value theorem to show that this equation has one solution inside the interval between 0 and 1. I want us to show that there is a solution to that equation, and that solution is a number somewhere between 0 and 1. Prove it to me. Now, you have to be careful. I am not asking you to find the solution. I'm asking you to prove to me that there is a solution between 0 and 1. All right. So what I'm going to do, I'm going to step away for a minute. I'm going to top off my coffee, and I'm going to let you think about this problem a little bit. But more importantly, I want to ask you, if I asked you to solve this, equation, could you? Forget the intermediate value theorem for a minute. If I put that on a quiz today in class, and I say solve that equation, could you do it? Okay, I'm just step away from that. I want you to think about that. Cosine x equals x. Do you have any tools in your toolbox of solving equations to be able to solve that? I'll take a minute and a half. I'll be right back. I just launched a poll to see if anyone here feels like they know how to solve this. There's no shame in saying no. Also, I plan on giving everyone here a little small bonus on the test for being present today. Because it was, change of plans, maybe a point or so on the test. So I'm going to take attendance based on your response to the poll. All right, let's get to this. I will end the poll and I will tell you what I've got here. I can share the results here. So you should be able to see that. 85% of you aren't quite sure how to do it. 15% feel like they got something. So, and I'm not gonna, when I do this attendance, I'm not gonna look at your response here and be like, call you out or anything here. So there's no way to solve this, okay? There's no way using anything that you all have ever learned, all right? So like, for example, if I try and solve this for X, you can't say it's already solved for X. You can't be like, oh, I've already solved for X. Because in order to know the value of X, you actually have to plug in X. So to know X, you have to plug in X, but you're trying to figure out what X is. So that's a circular argument. So you can't say it's already solved for X. The other thing you can't do is you can't come in here and take cosine inverse on both sides. Because even if you do that and kill off the cosine over here and get X, now the right-hand side is cosine inverse of X. So again, you can't solve for X unless you know X. So you're stuck in this circular argument. So there's just no technique that you have that can solve this. Now, if someone does think they have it, you can talk to me after class or office hours, but I'm pretty sure there's going to be a problem in your work. But that's the whole point of this example is to give you an example of an equation that does truly, in fact, have a solution, but that we can't do it by hand. All right, we can't. Does anyone want to make a comment before I move on? We're gonna keep working with this problem. Does anyone want to talk about the fact that it can't be solved or want clarification? Okay, so what I'm going to do now is I'm going to go to Wolfram Alpha and I'm going to ask it to solve that equation for us. I guess that's one way you could solve it, right? You say, hey, yeah, I can solve it. I just went to Wolfram Alpha and typed it in. So here we go. Boy, that was quick. It solved it, didn't it? X is approximately this answer. All right, so let me grab this. And let's take a look at that answer. It's saying that if you do that and you plug that X value into this, you should get a true, that should be a true equation. So what you do is take this number 0.7739085, you'd plug it into the cosine function on your calculator, you'd make sure you're in what mode? What mode would you have to be in if you're going to plug that number in? Radian or degree?
Radians.
Radian. The only time you ever use degree mode is if you know that angle that you're plugging in is a degree. So that it would have had to have had a degree symbol. Oh, what's going on? It would have had to have had a degree symbol up there for us to do degrees. Otherwise, everything's always in radians. So you can check yourself that if you plug that number in, it's going to be pretty close. It's not perfect because they round it here. So the question now becomes, how did the computer get that answer so quickly? And we can't do it, right? We can't do it. Well, let's bring in the intermediate value theorem. All right. So watch what I'm going to do, because this is weird. All right. What I'm going to do is I'm going to take this equation and I'm going to move everything to one side. So I subtract x on both sides and I have that right there. Okay. Now, what I'm going to do is I'm going to treat the left side of this equation like a function. I'm going to call that the function f of x. In other words, I am now defining this function f of x to be cosine x minus x. So let's say that I had started off this problem and I had given you all that I had given that function to you, okay? And then I asked you to set it equal to 0, right? Which is really this step. What would I really be asking you for on this function? Anytime you set a function equal to 0, what are you really doing? What are you finding graphically? When you set a function to 0, what are you actually looking at or trying to find on that graph?
Trying to find x.
The x intercepts. The x
Yeah,
intercepts. The x intercepts. You're trying to figure out where that graph hits the x-axis. So this right here is just a graph, right? We can graph that function. We can use a computer to do that if we wanted to. We could graph the function. And then this step right here is basically asking us for the x-intercepts of that graph. Right? And whatever the x-intercepts are, those x-intercepts are the solutions. It's the solution or solutions to this, right? So I'm trying to solve an equation, right? I'm trying to solve this equation here. So what I do is, oh man, I should have done this. Hold on, hang tight. Should have done this earlier. I forgot that I have this. Where's mouse? There is mouse. Pointers. I forgot I had this special mouse that you can see easier. So we started with an equation, right? You can do this. You can do this with any equation. You move everything to one side, which sets it equal to 0. You can treat the left side like a function. And then when you do that, the graph of this function, anywhere it hits the x-axis, would be a solution to that equation. Still with me?
Yes.
Okay. I'm trying to now show, let's go back to the thing. Well, I can write it down here. What we were trying to do is, the original question said to show that this has a solution in the interval 0, 1. So show me that there is an answer somewhere between 0 and 1 for this equation. Now, we've already looked at the computer, and the computer told us an answer, right? And notice that it is that number 0.739 is between 0 and 1, but we haven't shown that yet, right? We have not shown that. So now we're left with the task of trying to show that we do have a solution in here. So here comes the intermediate value theorem. Do you all agree that this is a continuous function on the interval 0, 1? So between 0 and 1, I know that this can be drawn without picking up my pencil. Can someone tell me why I know that? Can somebody tell me about the cosine function? Is the cosine
Oh yeah,
function?
because cosine is a continuous function.
Cosine's continuous. What about x? What does
It's
the
also
graph of
continuous.
x look like?
Straight line.
Straight line.
Diagonal.
And then
straight line.
I am doing what? I'm doing what with those two?
Subtracting them.
Subtracting. And we just said in the previous theorem that if you start with a continuous function and you subtract or add or multiply another continuous function, you stay continuous, like, so you don't lose the continuity. So I know that this is a continuous function, right? And I'm trying to figure out when this function hits the x-axis, right? So here's what I'm going to do. I'm going to take this function and I'm going to plug in the left endpoint. So I'm going to plug in 0 into this function. So we may need a calculator here. So if you have one, grab it. But for 0, this should be easy. If you plug in 0, you get cosine 0 minus 0. And we all know from pre-cal that cosine of 0 is
One.
Okay, so this is 1, right? That's 1. Now we need to plug in 1, don't we? Well, we got to plug 1 into this. This is going to be cosine of 1 in radian mode on your calculator, minus 1. Well, we could actually get our calculator out, couldn't we, and do this? But would you all agree with me that this number right here has got to be smaller than 1? Remember, the cosine function is this wave, and it goes between -1 and 1, right? So this number's got to be smaller than 1. And if you subtract 1, what can you tell me about this number? Is it going to be positive or negative?
Negative.
Negative. Everyone understand that? This right here is a negative number. Now, I guess I'll get my calculator out and I'll do it, but I really don't have to do this. Make sure I'm in radian mode. Quit. So cosine of 1, and then I subtract 1. On my calculator, I get negative 0.459, right? The key takeaway here is that this is a positive number and that this is a negative number, right? Which means if I were to graph this function, I know that at 0, I'm at a positive value up here at 1. And I know at 1, I'm down at a negative value down here somewhere. Why is that important?
Can you repeat that?
So what I've just determined is I've got a continuous function on this interval 0 to 1, right? And I know that when I start at the first endpoint at 0 at the left, I get the positive number 1. And then when I try and go to the right endpoint to 1, I know that I get a negative number, right? Why is that important when I'm trying to find the x-intercepts or the solutions to this equation? What do I know must happen?
It hits the x-axis.
I've got to hit the x-axis, right? Look, I don't know what the graph looks like, okay? I don't know. I do not know. I'm just going to guess. It looks something like this, okay? But I know that I've got to get from the yellow point to the green point. I know I've got to get from one point to the other. And I know I need to do it without picking up my pencil. And if I do it without picking up my pencil, I must cross the x-axis somewhere. I have to. The intermediate value theorem tells me that if I pick any n over here, right, any n I want, there's got to be something that goes to it, right? Well, what do I want to know? What n value am I interested in? The one that makes this thing 0, right? So I want to know my n is right here on the x-axis. And I want to know when that's 0. I want to know what that point is. The intermediate value theorem says that it definitely exists, doesn't it? It has to. So that has not helped me find the answer, but it at least tells me that it lives somewhere between 0 and 1, right? So I guess the key is the fact that this from here to here had a change in sign, right? It went from positive to negative. The only way you can go continuously from a positive number to a negative number is if you pass through 0. On the other hand, had it gone from negative to positive, we would still know we have an answer because you would go, the only way to go continuously from negative to positive is if you pass through 0. Okay. I want to recap it. It's hard with Zoom. I can't look at your faces and see if like y'all are asleep or you get it, or, you know, if I need to clarify. We started with an equation we couldn't solve. We moved everything over, set it equal to 0. We called the left side f. So now we have a function. And then when we think about it this way, this function has a graph. Anywhere it hits the x-axis would be where it's equal to 0, but that would correspond, those x-intercepts would correspond to the solutions to this equation. We looked at the function, we said it's continuous on that interval because we were trying to show there's at least one solution here. So we plugged in the left endpoint, plugged in the right endpoint, showed that there's a change in sign of those answers. And as soon as we show there's a change in sign, we know that it must be passed through 0, which means that there must be a solution to this equation. So I am done showing that there's at least one solution. The change in sign proves that to me. So on a quiz or a test or something, if I gave you a problem like this and I asked you to show that it has a solution, what you do is exactly this method. Move everything over, tell me it's continuous, plug in the left and right endpoints, and you better hope that there's a change in sign here. Now, the computer got the answer. We didn't get the answer. I wonder if anyone in here, is that a question, Ash, or no?
Yes. What do we do? What will we write if if it doesn't change in sign? Will we write just does not exist, or?
Very good question. Very good question. What would happen if it went plus plus, or what if it went minus minus? Would we give up? Well, I think I might answer that question with us going down this next road for the next 10 minutes or so. So think about this. The computer got the answer, right? All we know is that there is an answer in there. Can anyone think of what I could do now that would help me get closer to the answer?
Can you say that
Do
again?
this.
I'm saying, is there anything you can think of that I could do now? Now that I know that there's an answer between 0 and 1, is there anything that I could do to try and get closer to actually getting this answer? Because right now I just know the answer between 0 and 1. That's all I know.
Maybe take the difference.
Okay, you're on the right track now. Yes. Not difference, but I think you're thinking correctly here. We know it's between 0 and 1, right? So anyone else want to interject? Because I'm about to do it. I'm going to zoom in here. There's 1, here's 0. We know that it was up here and down here, right? But I don't know, again, I don't know what the picture looks like. Does it look like this? Does it look like this? Does it look like this? I don't know where it hits the x-axis. I have no idea. So why don't I do this? Why don't I cut it in half? And instead of looking between 0 and 1, let me look between 0 and a half. Let's focus all of our attention right now on this green zone. And let's do the exact same thing we just did. I'm going to copy this. And I'm going to plug in the 2 endpoints, but I'm only looking at the green. Okay, so I'm going to plug in 0 and a half. So I'm going to go cosine 0 minus 0, and then I'm going to go cosine of a half minus a half. So if you do the top one, we get 1, right, which is a positive number. And then if I go to my calculator and I do cosine of a half minus a half, I get a positive number. I get 0.377, whatever, who cares, it's positive. All right, what does that tell me?
You haven't hit the x-axis yet?
I have not hit the x-axis yet. That means my graph still looks like this. You see, I'm up here, which means what? the answer is where?
On the right side.
On the right side. Now, do you know where it is?
No, since you'll probably
No.
have to half again.
Let's half it again. Very good. See, this is you. I don't know how many of you are computer science majors, but this is like a computer science problem, because you're thinking about logically, could you program a computer to do what we're doing right now? So could you write code that would have your program check two endpoints, look for changes in signs, and then if you get a change in sign, half that interval and check the left side and right side. So we would now half this again. The number halfway would be 3/4, which is what, approximately 0.75, well, approximately, it's exactly 0.75, right? And so what I would do now is I'd say, hey, let's look just in this little interval right there. So I would check between a half and 3/4. And if you do that, we already know that this is 0.377, that's positive. And then if I do 0.75 on my calculator, so I'm plugging in 0.75 into the function, hey, I get a negative number. And what does that mean?
You hit the x-axis already?
Somewhere in there, right? Somewhere in there. So look, hey everyone, we've now narrowed it down to this window, right? It's somewhere between 0.5 and 0.75. So what should I do now?
Half it again?
Half it again and check again. For those of you who are computer science majors, can you imagine some program that keeps doing this like an iteration over and over and over? And what happens is each time we do this, it throws away half the interval. We threw away the left half, then we threw away the right half. If we did it again, it would throw away the left half. We would cut it in half, it would throw away the left half. We cut it in half, and we keep doing this. And what's happening is that window is narrowing down, isn't it? It's getting smaller and 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 smaller. I could have a computer do this millions of times in a fraction of a second. It could run this program and it'll take that interval down so small that what will happen is you'll basically be such a small interval that you can kind of approximate your answer because your interval is almost down to a single point. And that is exactly what happened when we went here and we got this answer. This computer, what it did in the blink of an eye, let's see if it's going to let me do this. In the blink of an eye, what it did is it got it down to an interval. And let's just imagine I'm zoomed in right now. And it said, okay, this is like 0.073 9084, and then over here it was 0.739086. And then it said, okay, well, these numbers are really close together. So what I'm going to do, the computer's saying, whoever wrote the code says, okay, once you get the interval down to a certain width, just go ahead and spit back the number right in the middle of those two, and just present that as the answer. Matthew, question?
Yes. Would the computer come up with several different answers if you plugged it in again, or no?
If the equation, so you know how I started this problem and I used 0, 1, right?
Yeah.
The computer is going to start with huge numbers. And then it's going to start checking, and it's going to, if your equation has more than one solution, it's going to find all of them. And for each one of the solutions, it's going to do this little cutting in half. And it all does it like super fast, right? I mean, we can't appreciate just how fast it does it, how many millions of computations are done in a fraction of a second. So it can get multiple answers. This method is actually, there's a name for this method. It's called the bisection method. It's one of the most primitive ways of finding the solution to an equation using a computer. There are actually more advanced methods that actually are faster than this method. I will show you one later in the semester if we actually have time. It's called Newton's method. But this is a really good introduction into understanding how it is that a computer can get that answer when we can't. It's using a very simple idea. It's using the intermediate value theorem. That's all it's doing. I want to show you one more thing. Right now, this answer is an approximation, right? That's an approximation. And whoever wrote the program, they said, again, when the window gets down so narrow, go ahead and just spit out the number right in the middle, and we'll say that's approximately the answer. But remember that window is tiny. That they've cut it up so many times, it's really, really infinitesimally small. Well, maybe I'm building aircraft parts or something. I need something even more precise, right? Something even better. Well, that tiny interval can keep on getting cut in half. So if you click on over here, more digits, you're going to tell the computer, hey, I need you to go further. I need you to actually keep cutting those things in half and give me more precision. Okay, let's see how long it takes. So now it's thinking. It's actually saying, okay, well, this is taking actually longer than it should. What is going on? I don't know why it's taking so long. Let me refresh the page. Okay, let me start. I'm going to hit enter, solved, got it, more digits. There, boom. You see that? It just kicked out more digits. Well, do you want more? I'll go more. I'll have the computer run the program even further. And I can keep going. How far do you want me to go? Well, now it's having a little bit of an issue. It's so small. The interval's so small, the computer practically thinks it's like, has no width to it. All right. That's kind of cool, huh? I'm out of time. So here's what I'd like for you to do. For your homework for this section, there's one problem I want you to avoid. And I believe it's the last one. Shoot, do I have my book? Let me grab my book. I'm sorry if you have to go. This is recorded. You can come back, but let me just grab my book real quick. All right. Yeah, so this section is, continuity, like I said, it's kind of like an interesting section, but it's not something that we're going to need to like be really understanding. What do I want from this? So for continuity, number 2, number 3 is fine. Number 4 is fine. Number 5 is fine. So I'm going to scratch some of this out. So 2, 3, 4, 5. I don't care about 11. The only other thing I want you to do. Don't worry about any of that. 43 and 44. So 2, 3, and 4 are kind of having you look at graphs and talk about continuity. And then 43 and 44, just like the problem I just did with solving an equation. So you move everything over and then you check to see if you get a change in sign. And when you're doing those, all you have to tell me at the end is, look, there's a change in sign, so I know the answer's in there. And you're done. Okay, everyone, again, thank you for your attendance and participation today. I will hopefully see you on Wednesday at school. Have a good one.
Would
Thanks,
you be
sir.
able to go
Thank you,
over
sir.
one homework question?
Yeah, absolutely.
It's for 21.